and welcome. I am revisiting my most popular video. For whatever reason, people like the methylamine video, so I thought I would explain the mechanism and what I was doing. I want to say the condenser I was using, 500mm air condenser, although it was cold outside, there was a risk of formaldehyde escaping through the pump. I can't give you a yield, but as this was a demonstration, I can confirm that this was a successful prep. It ends with me slowly evaporating a solution containing a significant amount of ammonium chloride, but some methylammonium chloride crystallized afterwards as a distinctly different fraction. It was hygroscopic and it had turned into a mush by the next day. One tip might be to add formaldehyde as you do this, because formaldehyde is the limiting reagent. Each molecule of methylamine requires 3 formaldehydes. I'll let you do the math. Let's get into it. Since today's compound contains nitrogen, I thought I would do a quick homage to Daniel Rutherford. I think it's Daniel. Yes, Daniel Rutherford discovered nitrogen in 1772. He sealed a mouse inside a jar. After the mouse died, he passed the gas through a solution that absorbed carbon dioxide. The gas that was left over did not support combustion or life, leading Rutherford to call it noxious air. Tablets.
Hello everybody. Hello everybody.
Hello everybody.
Hello, welcome back to another episode of Compound Interest. Today,
we're looking at classic chemistry.
Google tablets.
Today, hydrolysis and the polycyclic
Chemistry. 3D
rotating recycling bridge page. Commonly known
Hexamine is of historic significance since it was the first organic crystal to have its structure determined by X-ray diffraction almost 100 years ago. Agglomerated microcrystals connect and fuse together. Intercrystalline mother liquor become trapped, forming a symmetric pattern of solvent inclusions. It crystallizes in a body-centered cubic crystal structure, creating a highly symmetric dodecahedral morphology. Hexamine has inverse solubility, meaning the higher the temperature of the water, the less soluble it becomes. A saturated cold solution forms and agglomerate crystals on heating. For making methylamine, the process begins with acid hydrolysis. When hexamine is heated with concentrated hydrochloric acid, protons attack the lone pair of nitrogen. This weakens the carbon-nitrogen bonds, causing the cage to collapse. Hexamine, as indicated at the start, is, or at least was, sold as fuel tablets, sometimes in combination with
135-trioxane.
The reason being, this tube burns smokelessly and has a high energy density, usually with a coating of wax, which can be filtered off from an aqueous solution.
A polycyclic
Primer of
Formaldehyde. Upon burning, there is no melting, no smoke, and no residue left behind, ideally at least. Incomplete combustion can deposit small amounts of soot. Of soot. As well as small amounts of the less healthy gases, carbon monoxide, formaldehyde, and ammonia. Boiling under vacuum is a good idea because you don't want to exceed 100 degrees Celsius. In the real world, the reaction is not as simple as you may think. You get byproducts over hydrolysis. Instead of methylamine hydrochloride, you get ammonium chloride. Careful temperature control, careful measurements and weights serve to limit these losses. Unlike when you burn methylamine, in the absence of oxygen, you do get some nasty products. Hydrogen cyanide. Methylamine is a gas at room temperature. It shares properties and has similar character to that of liquid ammonia. It can be cooled to -6.3 degrees Celsius for use as a liquid solvent. It more closely resembles the smell of fish than pyridine, which smells more like decaying fish. But when you look into that, you find purer samples smell less like decay than technical grade, suggesting the smell is significantly adulterated by picolines. These are various methylated derivatives with a methyl group attached to one of the sites on the pyridine ring. But getting back to methylamine, when used in organic synthesis, it's considered more useful than ammonia because it is able to dissolve more organic molecules. Methylamine is to ammonia what methanol is to water. It is slightly less reactive than ammonia, but it forms acid salts such as the methylamine hydrochloride we are making here. Because methylamine is a gas, it's easier to handle in this form. It can easily be free-based when you want to bubble a dry stream of methylamine. Did I mention that formaldehyde forms during this reaction? For every 4 methylamines, 6 formaldehydes form. That is why I performed this outside. The reaction in more detail. First, the nitrogens are protonated by the acid. A 4:1 molar ratio of hydrochloric acid to hexamine was used. This excess of acid ensures that we protonate 1 bridgehead nitrogen on every hexamine. This gives the nitrogen a positive charge that pulls electron density from its neighboring methylene, and this weakens the carbon-nitrogen bond, allowing the lone pair on the oxygen of the water molecule to stage a nucleophilic attack on that methylene carbon. This opens up the first ring of the hexamine molecule and also creates an N-hydroxy methyl group, which is unstable and quickly loses a molecule of water to form a methylamine, which is further protonated to form a resonance stabilized iminium ion. This reaction creates a series of fragmented cage molecules, and eventually, with enough protons, we can sequester every nitrogen into a methylamine. But as I've already said, in practice, you end up with a lot of ammonium chloride. A very good yield would be over 80%. An average yield for somebody like me would be more like 40. In order to separate the ammonium chloride from our methylamine hydrochloride, fractional crystallization can be performed. The problem with this is it requires many recrystallizations because as something crystallizes, it includes molecules of the other substance within its crystal lattice. So things need to be dissolved again and crystallized again and again and again to get higher purity. Recrystallizing from 100% ethanol is the way to go because ammonium chloride is not soluble in ethanol, but methylamine hydrochloride is. Formalin boils at 96 degrees Celsius, meaning that at or above the boiling point of water, there will be unacceptable levels of formaldehyde loss. Formaldehyde will be key, as without its ability to reduce, our nitrogens will remain as the simpler ammonium chloride. Chemists aim for a temperature between 70 degrees and 85 degrees Celsius. This is both hot enough to break the cage, but also cool enough to retain reactants. The lone pair on the oxygen from a water molecule sets its sight on an electron-starved carbon of the methylene group on the weakened cage, and to form a double bond, the carbon is forced to let go of the nitrogen. Electrons are anti-symmetric fermions, and the Pauli exclusion principle forbids 2 identical electrons from occupying the same quantum state. When electron clouds overlap too much, the electrons are forced into higher energy configurations, producing strong repulsion. The result is a compact, tightly packed molecule, almost like a compressed spring at the molecular scale. Disturb that symmetry by breaking a single bond, and the whole structure quickly unravels. In other words, hexamine is a perfectly balanced molecular cage until the moment it isn't. What I'm about to talk about now explains the reason that hexamine is useful as a solid fuel, a component in explosives. It works as a treatment for urinary infections, kills bacteria through its production of formaldehyde in an acidic environment. The bladder. When hexamine loses just one single bond, all molecular symmetry is now lost, triggering a cascade of degradation. The integrity of this rigid tetrahedral cage came with a perfect balance of electrostatic repulsion and steric hindrance. Much of its energy comes from its geometric tension. To close the cage, the bond angles are pinched smaller than the 109.5 degree angles expected of a tetrahedral geometry. This is due to a compromise between the opposing forces, covalent constraint and van der Waals repulsion. For the angles to be wider, the bond lengths would need to be longer, and this costs too much energy. If the angles were any smaller, the van der Waals radii would overlap to the point where Pauli's exclusion principle will have something to say, or at least quantum mechanics will. In hexamine, the atoms are crowded, somewhat squished, with an angstrom of overlap in their van der Waals radii. This is the social distance safe space bubble. These are in fact closely tied to hybrid orbitals, regions of probability. Wherever this elusive electron is, if another one of its kind, an antisymmetric fermion, also wants to be there, one of them must jump up to a higher energy state, as they cannot both be in the same state in the same place. This equates to a compact molecule with a springy pent-up nature.